Alright, ladies and gentlemen, today we'll be starting on a new lab. The old labs that you may or may not be finished with, we will address that whole situation whether you are or are not done later when I'm in class. But today, I want you guys to work on this new lab with what we will call the pre-lab section, where you are writing up your background theory, your introduction, predictions, and whatnot. Also, you're going to work with this new topic, and that's kind of why I want you to do this today. I want you to explore the new topic. So let's talk about what's happening. This lab is about friction. We spoke very briefly about the topics of static and kinetic friction the other day. This lab can be done to show both, but we're going to focus solely on the static friction of it. So what you're going to have is you're going to have these little friction boats, and Mr. Emmer has those for you to look at. They're just these little plastic boxes, and on the bottom are three materials. There are some that have cork on the bottom, some that have this white plastic. It is technically called high-density polyethylene. You can call it white plastic for ease. Somewhere in the materials you might want to say high-density polyethylene. You might want to look that up, how to spell it. And the third one will have felt on the bottom. So you have these three different surfaces. So that's the thing you're going to be changing from lab to lab. In an aerial view, you're going to have forward. Sorry. Should have drawn the track. Oops. I guess I should be hitting the right button. There it is. In an aerial view, you're going to have the friction box, and you'll be putting weights into the friction boxes. You'll have the friction box, a short piece of string, and a force sensor. The force sensor, you will see, has a hook on it. Also has these two little holes that you can grab a hold of and pull onto it with. It may be useful to put the force sensor on a car on the track, just so that you are pulling steadily in terms of the angle you're pulling at, and hopefully your angle will be 0. So what you're going to do is you're going to ever so gently tug on the force sensor, and tug until finally it moves, and then you want to move at a constant velocity. And what you'll see happen when you do that is, when we hook it up to the force sensor of the computer, we'll have a force versus time graph. And on that force versus time graph, as you tug, you'll notice, and this is before it starts to move, you'll notice that the force is increasing. It's going to increase and increase until finally it gives way. That's the point right there. Give me the circle. Give me the circle, is the point at which it starts to move. That's the point we're caring about. If you then are able to pull with a constant velocity, you will have a constant force going on right there. Okay? You'll have a nice constant force. Technically, if we were studying kinetic friction, this straight line would be very useful to us. But this is the shape of the graph. And this point, the point at which it releases, is the point we care about. That is the maximum static friction point. That is the point that was the most friction could possibly contain until it gave way. And we're studying this topic of static friction. And I really want you to look up what that is. What does it mean? How does it work? Okay? So this point is what we're going to be looking for when we do it. So in your procedure, you're going to load up your car, and you're going to pull it, pull, and then finally it's going to move. That point when it finally moves right there is what we're looking for. In terms of trials, clearly each box is going to have its own set of trials. And each box is going to resist more or less, because, using up a word I kind of made up, they are more frictiony than each other. Yes, that's right, frictiony. You will also add weights to the boxes. Trial by trial, you will increase the weights until you have, in one set of runs, you'll have a very heavy box, and in some sets of runs, you'll have a very light box. Okay, and you'll do that for each one of them. So you repeat those. And we'll be studying this point, the point of maximum static friction. And there's this idea that we will come up with that I do not want to tell you yet, because I want you to discover it. So that's what we're doing. In recap, you have all three boxes: cork, high-density polyethylene, and felt. You will run multiple trials. These trials will include progressively heavier boxes. You'll repeat that with each one. And of course you need to do multiples for every box. Especially on this lab, it's very easy to get goofy data. So you'll do multiple trials with multiple weights with all three boxes, and you'll gather this very, very important idea that we'll talk about later from the lab. In terms of prediction, the thing that we're going to increase per box, and that's kind of how you're going to have to word your prediction, because you would imagine that friction is going to at least behave the same way in all three boxes. It's just that your value will be different. That as you increase the weights, you need to make a prediction about, as I increase the weights, what's going to happen to perhaps the force of friction necessary to break the static friction, or the applied force necessary to break the static friction. Maybe that could be your prediction. As you increase the weights, something happens to the applied force. Okay. If you want to make a prediction as to which boxes, maybe you want to rank order the boxes in their frictioniness. Yes, another made-up word. Maybe you think the felt will be the most frictiony and the cork will be the least frictiony. Now that's up to you. So again, when you're planning out, you're going to pull gently, 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 pulling and increasing the pull until finally it gives way and it moves down the track. Okay? You're going to work on these labs, and yes, we will revisit the other labs to make sure that you are getting those done. And I'll come around to each group and everything and look at your work, and it'll be great. But today, I want everyone to work on this, and I will be checking your progress on either tomorrow or Wednesday. I will be checking your progress. Good luck.